The thing that I say in the email right up front, and the thing that I reemphasize in this room, is that exam grades are not value judgments, even when the exam is called an assessment. This average did come in very, very low. It came in very, very low, even though the assessment was open book, open note, open internet. And I made very plain, I was not using proctoring software of any sort. So, and the evidences of irregularities were nil. Okay. Just so that people can know that this can be done, and I get a little bit of a swelled head about being able to do it. But I will talk to other people about how I actually design things like this at any point in time. If you have a professor who doesn't like using the proctoring stuff and wants to know how we can avoid using the proctoring stuff. Note how I put the A's and B's and C's and D's. If I was just on a 90, 80, 70, 60 scale, here would be, everything here would be F's. And everything there is not F's. Okay? I am not 100% convinced that's not a B. Okay? I'm not 100% convinced that these aren't F's. But we will see. I know that this is an A. I'm very sure that's an A. These might be B's. Okay. And the communication that comes out of this is everybody in the room has stuff that they can improve on when it comes to the problem solving. Okay. You may have wound up in this position because there are particular ideas that you don't understand. You may have wound up in this position because you understand a lot of things pretty well, but taking 20 multiple choice questions in 30 minutes with computation required may have been a lot. You may have wound up in this position because you understand core ideas well, but at the point where I ask you to think on your feet and apply those core situations to something that is not an easily Googleable concept, that was the point where you fell through the cracks. Okay? Any number of different things may have led you to this. Okay? But the way out of this for many of you is doing the work and understanding the concepts by practicing the concepts to get there. The thing that is more worrying to me is not these marks that are in front of you, it's the homework rates for the course. And the midterm marks are going to be largely based on those homework rates. And if you've got homework that you need to catch up on, that's going to be the thing that is the major tell for you as far as midterm marks is concerned. Go, Nate. Midterm grades will go in midday tomorrow. I'll turn them in at the last possible moment. Okay? So if you want to get some extra homework done before I make that report, by all means, I will use every cynical excuse to encourage the population to do more homework, except actually set due dates on the thing, because ultimately I still believe that it's not an issue of when you actually do the homework and when you understand the ideas. It's an issue of that it happens before the end of the term. I do have the Alex practice included. I have it included in full. There's a lot of folk who haven't done a substantial amount of practice in Alex. That does need to come up as well. You will find there are very specific algebraic reasons in the problem solving that is ahead of us for you to be into ALEKS and doing that ALEKS practice as well. Because algebraic instinct is going to start to matter a little bit here. Okay? Any other questions about grades at present? The point where I apply the curve for the course is at the end of the course. Right now, I leave these grades stand as they are. But when we get through 3 assessments, and then when we have the corrective effect of an ACS final that only helps final grades, it doesn't harm them. At that point in time, I actually then go through and make adjustments to what is considered an A, what's considered a B, et cetera, et cetera. Okay? But now is not the time to panic. Even if you wound up down here in this territory, now is not the time to panic. Now is simply the time to redouble efforts. The other benefit to an exam that has an average of that's this low is that there is room for these marks to improve, and there's room for the curve to take hold in ways that nobody came up here and wrecked. This is a good paper. It's a very good paper. It also had some key errors and key misunderstandings. Everybody has the capacity to improve. Everybody should take advantage of that. Okay? Other questions, other concerns? We're talking about equilibrium. In the interest of talking about equilibrium, I want to show off one more time an example of an equilibrium reaction. These 2 containers of nitrogen dioxide that this Professor Burke goes and takes one of them and puts it on ice, buries it in ice to make it cool down, and then goes on about his time of lecturing, then makes a key point about the nature of temperature shifts of equilibrium. And I'm going to try to come back over here and catch Burke coming over and actually taking the bottle of NO2 out of the container and showing off that the equilibrium has shifted and that he has a lighter, more closely to colorless gas in that container, and it's more gone to N2O4. And you can see, again, that's my favorite angle to show that off at. You can see on the left what the majority NO2 container looks like. You can see on the right what the container with substantial quantities of N2O4 looks like. And the thing that I want to impress upon you today from the viewing of this example is that the reaction shifted and the change happened because that container that you see up here on the right that was put under ice was stressed. It was at a situation where it was at room temperature and it was dunked in ice and it was stressed in such a way that the system could do chemistry that responded to the stress. And this is one of the core principles of equilibrium chemistry that we want to make sure we have expressed. This is a statement known as Le Chatelier's principle. Le Chatelier is a French name. If I'm going to be really appropriate with it, I need to take this A and put a little bitty hat over it like so. That actually looks like it belongs with the font. I'm pleased with that. Le Chatelier's principle. When a system at chemical equilibrium is exposed to a stress, the system will respond in such a way that reduces the stress. This is one of the most fundamental principles of chemical equilibrium. It is so fundamental that I want to take our lab time together next week and completely focus on Le Chatelier's principle and focus on it in such a way that I'm going to break against my type and not employ a Google Sheet from the study of it at all. That's me saying, okay, this idea is important enough that I want to keep my personal safety away from it. Let's put the equation for the NO2 N2O4 system back up. I'm going to stick over here standard delta H for this system. In the exact same way that Burke had that on his screen in that video of the NO2 N2O4 system. What does that value of delta H mean? When I have a negative value of delta H, does that mean that heat is going to be absorbed by the system or released by the system? Definitely released. Does that mean this reaction is exothermic or endothermic? Exothermic. Heat released by a reacting system is an exothermic reaction. Okay? What we just saw in the video was an example of stress to the system. The stress to the system is that the system was placed on ice. The system was suddenly cooled. The ice surrounding the thing forced the system to have to forced an absorption of heat. So how does the system respond to that stress? The ice is sitting there, the ice is absorbing heat. What's that? Well, it's a gas already, so the ice is going to melt, but the ice is not the system that I care about. The system that I care about is inside that bottle. It's the gases that are in that bottle that are going to be responding to that stress. And the system's certainly going to contribute to making that ice melt. The system is going to release heat. And you can write out reaction instead of abbreviating reaction RxN if you want to. I'm just trying to conserve space on my whiteboard. Now, when this system releases heat through going through this chemical reaction, the result of that release of heat is going to be what? It's going to be the generation of N2O4. It's going to be the reaction moving forward in a way that releases heat. Okay? In the language of equilibrium, we have a very precise way that we say this. We say the equilibrium shifts to the right because the process of this reaction going forward, the generation of products in this reaction, gets me heat release. Everybody can still see my implied kilojoules per mole back here, right? I'm going to keep it hidden back here behind my icons while I talk about a different stress that I could put on this system. You might not notice it a whole lot, but then as the video moves forward, our hero, the professor, is going to do various things to have these bottles waving around the room and have this very cold bottle now being restored to room temperature, brushing off the ice, holding it with his hand. Okay? And over a period of time, he's going to have the containers relax themselves, and he's going to have the containers come closer to the same color. I see the color of these guys at the, I don't see the color of these guys at the end. Yeah, but you can already see that there's a little bit of returning of the original color in this container and this snapshot of the bottles from a little bit later in the video progress. That also represents a stress. System heats up. Now, when the system was placed on ice, the response to the stress was the system releasing heat through reaction. So if the system is heated up, what do you suppose the response is going to be to that stress? Heat isn't going to be released, heat is going to be absorbed. I had a little more room this time, so I wrote out reaction. Well, we've already established that this reaction moving forward is exothermic. This reaction moving forward is responsible for releasing heat. So how do I make this reaction endothermic? Reverse it the other way, sure. I make sure that I can take the reactants that I have present that made this container more colorless and allow them to regenerate the nitrogen dioxide we started with, making the container brown again. Well, we'll call that an equilibrium. Shifting to the left. We'll generate reactants to absorb heat. Makes sense how this system's responding to the absence of the removal of heat energy or the transfer of heat energy into it. This makes sense. Stressing a chemical system, though, is not merely about the stress of temperature, heating up the system or cooling down the system. Let me copy this so I can go further down the page and make some other ideas clear. One of these days I'll be able to copy and paste these reactions smoothly. That's not it. There we go. Still working on the same reaction. Let me stress this reaction by suddenly taking the bottle that gas is in and opening up a tube to the bottle or opening it up to the surrounding area. Let me suddenly increase the volume available to the gases. Well, if I've got a gas in a confined container, and it doesn't seem like that's a big stress, does it? It seems like that's the reverse of stress. I've just relaxed the constraints on the gas that are available to it. But it is something that the system is definitely going to respond to. I'm going to take this gas tightened up in a container, and I'm suddenly going to make it available to a whole bigger volume. Okay? How does the gas system respond to that? It wasn't confined space. I open up a whole lot more volume. What's the gas going to do? It's got to fill up the volume. And the gas is specifically going to change in order to best or most readily fill up the volume. Now, question. Which side of this which side of this chemical reaction has more gas on it? The left side or the right side? I got an answer in the chat. What does the chat say? Come back here. The right side, that's the answer I got this morning too when I asked the population this. N2O4 certainly is a bigger molecule. It certainly is more complex. There's more to that molecule. But it's a single gas molecule. It actually turns out that the left side of this equation has more gas on it. And the rationale for saying that the left side of the equation has more gas on it is the coefficient in front of NO2. NO2 is a smaller, simpler molecule, but there are more of them. This falls right in line with the question I asked a couple weeks ago, which side of this particular equation is more disordered. And we said it was the left side of the equation because there are more molecules broken up that are capable of filling up more space. So when I actually have this sudden increase in volume, the result of that is a shift of the equilibrium to the left. More gas molecules are generated to fill the volume. And that might actually be easier to think about when you think about the opposite stress. Taking a container like this and suddenly decreasing the volume available. Well, the change in the gas that has to happen in that circumstance has to be a change in the gas that will fill as little volume as possible. And that stress is going to take the molecules of NO2 and shove them together to make N2O4. If you were to suddenly decrease the volume available to the gas, you would find that this gas would turn colorless because you're generating the gas molecules, even the bigger gas molecules, but they're gas molecules, they'll take up the least amount of space because there are fewer of them on the right than there are on the left. So you change volume, you're wondering what happens to a chemical equilibrium. When that happens, look for the side of the equation with more molecules of gas. Look for the side of the equation with fewer molecules of gas. One more example of stress here. Let's say that what I do is introduce a mass amount of NO2 to the reaction mixture. I was at equilibrium. I was roughly sitting equal-ish between these amounts of stuff. Let me change this system in such a way where I just pile on the NO2. And the stress is I got a lot of NO2 running around. Well, if the stress is I got a lot of NO2 running around, what's going to be the way I reduce the stress? If the stress is having a lot of NO2 around, the response is going to be get rid of the NO2, right? Run the reaction in such a way that it eliminates the presence of NO2. So how do I go about getting rid of the NO2? Smash molecules together, get N2O4. And that's going to represent a shift of the equilibrium to the right. And a reaction that shifts that equilibrium to the right is going to eliminate NO2, and it's going to generate N2O4. And the opposite stress goes the opposite way. If I suddenly introduce a mass quantity of N2O4, I'm going to react to eliminate N2O4's presence, and that takes this equilibrium up here and shifts it to the left, eliminating N2O4, generating NO2. When a system is stressed, the system responds in such a way that reduces the stress. Clear to everybody what I mean when I say the equilibrium shifts to the left and the equilibrium shifts to the right? And again, when we get into the lab next week, we'll do more examples of this with real chemical stuff in front of us so that we can actually have a better sense of what it means for these types of equilibriums to go through these shifts. Okay? Now, of course, I got to be me. And because I got to be me, I'm not just going to deal with this conceptually, I'm going to deal with this computationally as well. And I want to make sure that I have an example in front of you that gives you a sense of what I mean by equilibrium shifting to the right or equilibrium shifting to the left from mathematical view. So let me put an example on the whiteboard here and go through an example. Let's see how good I can get this typed in. NOCl. It's a compound that does what it looks like it does. It's a compound with nitrogen, oxygen, and chlorine in that order. I should know the actual name of it. I don't. I'll just call it NOCl. And K is relevant to this reaction that I'm going to write on the board right here. Now, how many folk have dove into the practice of doing equilibrium constants for reactions of this sort? If you haven't dove into that yet, you need to, because it's going to be one of the core skills that we're going to be working on going forward here. What is the expression for the equilibrium constant for this particular reaction? Everybody in the gas phase, nobody is activity of one. Any equilibrium product is going to be what quantities over what quantities? Products over reactants. So the products I have in this reaction is going to be the concentration of NO. What do I do with the concentration of NO? I better square it because of the 2 coefficient right here. And then Cl2, what do I do with the coefficient with the power of Cl2? Nothing necessary, I just have the implied 1 here. Okay? And then I have NOCl as a reactant. I have a coefficient of 2 here. So I better square. Okay? Now, before we talk about what we know, let's talk about the setup of this particular problem. Okay, we're starting with a 1 mole sample of NOCl. Does it say anything else is present initially? not a blame thing. So we're just starting with 1 mole of NaOCl in this 2-liter reactor. Okay? So it's all reactants, no products. Which direction is this equilibrium going to shift? Well, it better shift in a way that I'm going to make some products, right? And in fact, it does say that it shifted in a way that we made some products. But we say that this is an equilibrium that's shifting to the right as the reaction is going forward. Because we're starting with all 1 reactant. And we are moving forward with the chemical reaction as we increase temperature. Getting more products out. Okay? Now, what does the problem tell us that we know? We know a temperature. Now, at some point in time, I may want to have that temperature not in degrees Celsius, but in Kelvin. What's 227 degrees Celsius in Kelvin? Here's a hint. 227 degrees Celsius is a temperature that's really liked a lot. Because 227 and 273 add up to what? 500, bang on. Yep. Strictly speaking, though, it's plus 273.15. So I'm going to call that 500.15 Kelvin. If I wind up using that temperature, though, I'm going to wind up using it much later in Kelvin. If all goes well, I'll actually bring up what I do with that temperature later on. But for the moment, the temperature is the least important of these quantities that I'm working with. What else do I know? I know moles of what? Okay. Let me put this like so. Okay? Now, when I have this up here and I have all of these guys in brackets, they don't represent moles, though. What do they represent? They represent concentrations in what units? How do I measure concentration? How did I do it in Gen Chem 1? Not molar mass, but definitely moles per. Not kilojoules per mole, not per gram, per liter. Concentrations, moles per liter. Okay? Oh, yay. Not only do I have a volume of this container, but the volume of this container is a nice round number. So the concentration of Cl2 is going to be 0.056 mole of Cl2 divided by the 2-liter container. And that gets me out molarity units. And 0.056 over 2 is going to be what? And I write that as molarity. But when do we know we have 0.056 moles of Cl2? Because we did all of our stuff here and we did the system reaching equilibrium and then we analyzed the contents of the reactor. So this is at equilibrium. I mean, that's nice. Okay, we know that we can use this value of Cl2 in this reaction. Okay. But here's the thing. What's the other concentration we have here? The other number of moles we're given? NaCl. I can totally compute that, right? 1.00 mole over 2.00 liters. I mean, you don't even have to use your calculator for that, right? And when do we know that particular concentration of NaCl? Hint. Not at equilibrium. Because that's the amount of NaCl we've got right at the very beginning, right? So what this problem is doing is it's outlining two different times that we know two different quantities in this reaction, one of which is great for an equilibrium expression and one of which most certainly is not. And it still says I should be able to know all the other things and come up with an equilibrium constant. Well, what do I do now? What I do now is go back to stoichiometry. Now, I've got to do stoichiometry for everybody. But I have to both do the moles to moles for everybody. And then I have to come up with how that number of moles is changing and do limiting reactant sort of tails for everybody. And if you remember how much effort we put into stoichiometry in Gen Chem 1, you can see very quickly how this could become a royal pain in the keister. So what I want to do with the stoichiometry in this course is I want to organize our work. And I want to organize our work into a chart. And I want that chart to tell as many different details about this progress of the stoichiometry of this reaction, where we're starting with 0.500 molar concentration of NaCl, and we're ending up with 0.00028 molar concentration of Cl2. I want to fill in all of the other details as precisely as I can. quick word from our sponsor before we go forward. Not only have I given you the links to your textbook and examples in your textbook that have stories like this in it, I've given links to a different open textbook that has a whole lot more examples in it, including this very example right here. And all of those examples have this type of chart we're going to build for the purposes of our problem solving. I want you to get acquainted with the building of this chart. I want the building of this chart to become a bit of second nature to you. Okay? Here's what the chart's going to look like. It's going to be a chart of 3 rows and 3 columns with headers on each side. So I'm going to build it like this. 2, 3. Give me a little more room for the building here. 1, 2, 3. And the columns are going to go as the concentrations of each member of the reaction in order. The first heading is going to be NOCl concentration. And the second heading is going to be NO concentration. And the third heading is going to be Cl2 concentration. And the first row of the table is going to talk about initial values. Now, I've already talked through the problem. I've already mentioned the fact that we got initial. Okay? We computed the initial value for NOCl concentration right up front. And we said that we had NOCl, and how much of the 2 products did we have when we started? Is there anything mentioned about the products when we start the problem? No, it just says we put 1 mole of the NOCl sample into a 2-liter reactor. So I got nothing and nothing there. That's my first row. My second row is going to talk about the change that's present as this reaction goes forward. Now, I already know a little something about the change that's going to happen to Cl2. But in order to keep that algebraically profound, I'm going to describe the change to Cl2 as being some plus X. I'm adding X amount of Cl2 to this reaction mixture as I go to equilibrium. And I just choose to represent this as plus X because I have 1 mole of Cl2 being generated in the reaction. So how do you think I'm going to write the change for NO in that context? It won't be plus X. For every 1 mole of Cl2 I generate how much NO? 2 moles. So what's going to go down here? Not X, 2X. Now, this is happening because of reaction progress to the right. I'm generating NO in Cl2. Where did the material to generate NO in Cl2 come from? It comes from the NaCl. So what's changing about the NaCl? Is the amount of NaCl increasing or decreasing? It better be decreasing, so I better have a negative here. What comes after the negative? Take a guess. Not negative X. Here is the 2 again. 2 moles of NaCl generate 2 moles of NO plus 1 mole of Cl2. The coefficients of the change quantities come from the coefficients of the chemical reaction. And the signs given by the way the reaction is shifting. If the reaction is shifting to the right, all of the products are positive, the reactant is negative. If for some reason this reaction was shifting to the left, then all the products would be negative, the reactant would be positive. Okay? Does everybody see the significance of this change line in this table? Well, the value I haven't used yet is what? I've not used the 0.028 yet. And the 0.028 represents what? It represents the final value or the equilibrium value of Cl2. I could call this last row final, but it's not quite as poetic if I do so. So I call it equilibrium. And this will be the point where I plug in the other known. And 0 plus 2x here is 2x here. And 0.5 molar minus 2x is something I'm going to write down as so. And this is a filled-in tabulation. It's a tabulation that's going to let me do some simple algebra to find out the equilibrium values of the other guys. Because looking at this table, I know what x is equal to, right? By adding x, I got 0.28. For Cl2, 0 plus X equals 0.028 mole. And because I know X for that column, I know X for everybody. What's the concentration of NO in this case? How do I go about computing the concentration of NO? Yeah, 2.2 times 0.028 mole. That better get me 0.056 mole. And then compute the concentration of NaCl as 0.500 molar minus 2x, which is 0.500 molar minus 0.056 molar. Last hour, I looked at that for just a moment and I said, that's really obnoxious. The person who set up this problem could have chosen some better numbers. And they're my equilibrium values that I need. That wasn't terribly oppressive algebra, was it? It's doable. But the algebra emerged from this charting of the values at initial conditions through the change and at equilibrium. We'll call this frequently, for simplicity, an ICE table. ICE, initial change in equilibrium. We will construct ICE tables like this frequently over the course of the next couple of weeks to help us solve equilibrium problems. In general circumstances, for gases and solutions, and then in the really precise circumstances that are biologically relevant of acid-base chemistry. We'll come back to these ICE tables again and again and again because they tell us such detail about stoichiometry in a compact way that hasn't been characteristic of any of the problem solving we've done to this point. Okay? Does everybody understand what goes into the setup of these? Well, what we set this up for was to have equilibrium values of everybody here so we could solve for this equilibrium constant. So let's go ahead and do that real quick. Now, one thing that I wind up doing when I plug these in, everybody's noticed that I have a real bad way to be obnoxious about units, right? And making sure units are included in everything, canceling out units when they are appropriate. Notice that I'm going to write stuff in here without units. I'm going to write stuff in here without units because these concentrations represent activities of the individual participants in this story. And these activities are unitless, and equilibrium constants are presented as unitless as well. 0.056 squared times 0.028 divided by 0.444 squared. And that gets me a constant of 0.00044454. I'm going to err on the side of too many significant figures. Quick question. Standard conditions, is this a spontaneous reaction or is this a non-spontaneous reaction? Let me do one other calculation before I let you go. Nate, after all, pointed out that we knew the temperature. I don't need to let Nate go without having some means to use the temperature. Let me bring out this particular equation we showed at the very end of our time together on Tuesday. And this is our means to connect free energy of a reactant, of a reaction, to the equilibrium constant for that reaction. Now, remember, when we do this calculation, the value of R that we're going to wind up using is going to be our joules per mole per Kelvin value. It's going to be 8.314 joules per mole per Kelvin. But like Nate said, we do know this temperature of this reaction, the 500.15 Kelvin. And we do have the equilibrium constant, so we can actually compute the natural log of that. Natural log of answer is going to be negative 7.7. Negative 7.7 times 500.15 times 8.314 times the negative 1 in front. And that's going to give me a standard delta G of 32,087 joules per mole. Just joules per mole because the equilibrium constant is unitless. Its natural log is unitless and the kelvins cancel out. I usually write these in kilojoules per mole. To go from joules to kilojoules, I need to do what? Divide by 1,000. Thank you so much. We'll just rise 32 kilojoules per mole. Rather positive delta G, spontaneous or non-spontaneous? Remember, it's negative delta G's that correspond to spontaneous reactions. This reaction, under standard conditions, is non-spontaneous. But it moved forward initially. I mean, it still went forward. It still got us products. How did I do that calculation? Okay. Go back one more time. This particular delta G story, negative R times T times natural log of K. The natural log is something that you should have on your calculator. And I said it before, the natural log of 4.454 times 10 to the minus fourth should come out to be something like negative 7.7. You want to look and make sure that you've got on your calculator a means to do that. And if you're stuck on how to do that natural log on your calculator, let me know either in lab this afternoon or as we get back together on Tuesday, and I'll see if I can be a little bit more demonstrative with that. Okay. 8.314 is a constant. It is our new value of R in joules per mole per Kelvin. And I'll make sure I re-emphasize as we go on Tuesday that R is a constant. And the temperature is the temperature that we had at the start, 227 degrees Celsius converted to Kelvin. Okay. I know this natural log thing is something that is very, very new to a lot of you. And I want you doing mathematical practice for many reasons, like recognizing these new things. Okay. The homework that's up will help you through a lot of that. And as you get stuck on homework, let me know, or let one of the tutors in the tutoring center know. Homework is going to be, like I said before, one of the key determinants of where your grade is coming forward. And the course is getting more mathematical from here. So the homework practice and getting help when you get stuck on the homework practice is going to be math. Okay? And keep asking questions. Even if we're limited on how the questions are going to be answered on Zoom, I'm very, very welcoming of those questions. And I totally want to hear those questions again in the lab session if you still got it, okay? Thank y'all.
Hey, Dr. Pearson.
Hey,
Is it okay if I stay after real quick and just ask you a question?
yeah. Let's see if we can get everybody else bailed out of here. Of course, if you're going to ask a question, I better stop the recording.